So today in this video, we'll discuss about the adiabatic relationship between pressure, volume and temperature. We know that in an adiabatic system, the external heat is not allowed to come in, or the inside heat is not allowed to go out. It's not allowed in an adiabatic valve. So heat exchange is not possible in a adiabatic system. So here we can write dq is 0 in case of a adiabatic case. So here in this video we'll derive the relationship between P and V first. Then we'll find out the relationship between pressure and temperature, and finally we'll derive the the relationship between volume and temperature. So basically in this video we'll derive P V to the power gamma is equal to constant, very important relationship. Then we'll also derive P 1 minus gamma T to the power gamma is a constant, and also we'll derive T D to the power gamma minus 1 is equal to constant. So all these three derivations we'll do in this video. We'll derive one by one. The first one will derive P V to the power gamma is equal to constant in the beginning. So the first relationship is the relationship between pressure and volume here. So how we will progress? So to begin with, we'll start from the first law of thermodynamics. All of us know that the first law of thermodynamics states that if the heat supplied is dq, then this amount of heat will change the internal energy of the system, and it will do some work. Either it will expand the system or it will compress the system. So some work will be done on the system. So this amount of heat supplied to the system will do some work, will change the internal energy. du is the change of internal energy, and dw, it will do some work. So this is the first law of thermodynamics. From first law of thermodynamics. So from first law of thermodynamics, we have written here that dq is equal to du plus dw. Now you know that here dq is 0 because we are discussing the case of adiabatic expansion, adiabatic system we are talking about. So in case of adiabatic system, the heat exchange is not allowed, and we can say that dq is 0, right? So this expression will now convert to 0 is equal to du, I can write cv dt, plus dw I can write c dv. How? I think all of you know this, that for 1 mole of substance we can write 1 by mu du by dt, constant volume is your cv, specific heat capacity. This is the relationship between cv and your internal energy du. Okay, so this is the formula. For 1 mole of gas we can write mu is equal to 1. Okay, so this will convert to, and volume we can, because we can means if we'll not write also volume, it's okay. So here we can write like this, the du means it's you can understand this one. So du is equal to cv dt. This is what I have written, du is equal to cv dt, right, for constant volume, and dw is equal to p dv. We know work done can be expressed in terms of change in volume and your pressure, right? Now this is, let's say, equation number 1. Now, and this is we have done for 1 mole of gas, remember, because we have put number of mole is equal to 1. So here I have done for this expression I have derived for 1 mole of gas, right? Now from the ideal gas equation of 1 mole, ideal gas equation. Okay, from ideal gas equation you can write that PV is equal to RT. Mu RT or nRT, number of mole is there of course, but here we are discussing about 1 mole. So one number of mole I have taken is 1, so I can write PV is equal to RT. Now if I differentiate both sides, then I will get PdV plus VdP RdT, right? So here I am differentiating, right? And this volume and pressure, they are means not constant here, both are means variable. So I have to, once I have to find out the derivative of V plus derivative of P. Okay, product rule you can use for the differential case, and R is the constant, it will come outside, so derivative of T, because the temperature will also, if it is expanding, temperature will go down, if it is compressing, then temperature will go up, right? Now we have this relationship. Now we'll just simplify and rearrange it, and we will find out this relationship, the first relationship, that is PV to the power gamma is equal to 1. Now how you will rearrange it? Now from here you can get that information that your dt will be equal to R. I can divide here, so your dt will be PdV plus VdP by R. So this is your dt. Now I'll put this dt in our equation number 1 here. Okay, in our equation number 1 I'll put this value of dt, and the equation 1 will now become equation 1 will convert to, okay, that Cv dt is equal to this one, PdV plus VdP by R is equal plus PdV equal to 0, right? Now just to multiply, find out the LCM and simplify the equation. Cv dV plus VdP, R LCM, so Rp dV is equal to 0. R I multiplied with 0 in the right side, so it's 0. Now you can write, you can see PdV common here, so I can take common Cv, here R will be there, common PdV plus VdP is equal to 0, right? So here you can do, here you can write like this, Cv plus R. What is Cv plus R? We know one relationship, if you remember, that Cp minus Cv is equal to R. For 1 mole gas, if it is a number of, if 2 mole gas, then it will be 2R, NR. Actually, relationship is NR. For 1 mole of gas, it is only R. Cp minus Cv is equal to R. Or you can write Cp is equal to Cv plus R. You can write this, right? So I can write Cv plus R as Cp PdV plus VdP. Okay, Cv VdP. This is Cv VdP, or Cv I have left, Cv VdP. So Cv VdP is equal to 0. Now I'll divide PV both sides. Okay, both sides I'll divide PV. That means I'll divide PV here and PV here in the right side, 0 by something 0. So if I'll divide PV both sides, then what shall I get? Okay, what shall I get? I'll get this one PV, PP cancel out, V, so this will be Cp dV by V plus VV cancel out, so Cv dp by p equal to 0. Okay. Now here what we have done, here we have separated the variables db by b by dividing what we have done. By dividing pb, we have done one thing, that is we have separated the variables dp by p, db by b. Okay, and these are the constants, right? cb and cp, these are the constants. So what we will do now, we'll integrate, and now we'll integrate and we'll see. So now we'll integrate that cp integration db by b plus cb integration dp by b equal to 0. So this one will be cp log base ev ln v, right, plus cb log e log e c is equal to derivative of 0 is a constant. Integration of 0 is a constant. Now you can write in this way. Okay. What I'll do, I'll divide cb both sides now. What I'll do, I'll divide cb both sides. Then what you will get? cp by cb log ev plus log ep is constant, right? Is constant, because see, this is a constant, so it will be another constant. You can write this one cb, and cp by cb we know that it's a ratio, and we say cp by cb is a gamma, this another constant. So what we will write, so this will be gamma, right, log ev plus log ep ac, constant. Now you know that if coefficient of logarithm will be the power here, right? So I can write, if I'll remove this coefficient, it will become b to the power gamma. And also this rule we know, that log a plus log b is log ab. We know this relationship. So here we can write, using this algebra of logarithm, we can write that this is log e, this one will be b to the power gamma, and will multiply by p. So p b to the power gamma is equal to c. Or if you want to remove this log e ln, then here it will be in the right side e to the power c. So it will be p b to the power gamma is equal to e to the power c is a constant. Okay, constant. This is what we are supposed to prove, that in an adiabatic system the relationship between pressure and volume is a constant, and it is, this one is a gamma, cp by cb. So p b to the power gamma is equal to constant. This is what we are supposed to derive for the first relationship between pressure and volume in the case of a adiabatic system in your relationship between pressure and volume. Okay, so now next the second relationship we will derive. The second relationship is second relationship we will derive between pressure and temperature. Pressure and temperature. We got the relationship p v to the power gamma is equal to constant. Now we'll do p pressure and temperature. So to find the relationship between pressure and temperature for an adiabatic case, what we'll do? We'll use this relationship p v to the power gamma is equal to constant, and from ideal gas equation we know that From ideal gas equation, we know that PV is equal to RT. Or you can write, here you want to remove what? You want to remove volume and you want to introduce temperature. So I'll write volume is equal to, because my target is to remove volume, so I want to replace volume. So V is equal to RT by P. Now I'll replace this V here and I'll get another relationship between pressure and temperature. So what shall I do? I'll put the putting V in P V to the power gamma is equal to constant. What I'll get? P V is this one, RT upon P all to the power gamma is constant, right? So this is what you can simplify. So this is P divided by P to the power gamma, that means 1 minus gamma, and T to the power gamma, and R to the power gamma is equal to constant. Now this R to the power gamma is a constant. I'll divide here. So I'll write like this: P to the power 1 minus gamma T to the power gamma is equal to K R to the power gamma. So this is another constant. So I can write P 1 minus T to the power 1 minus gamma T to the power gamma is a constant. So this is your relation 2 that we are supposed to prove, that P to the power 1 minus gamma T to the power gamma is equal to a constant. Now the third relationship and the last relationship we will prove, that is between temperature and volume. So the relationship between temperature and volume will proceed exactly in the same way, only I'll change here, like I will find the relationship P is equal to RT by V. Then I'll get the same thing I'll do, okay? Same thing I'll do, putting in same equation P V to the power gamma is equal to constant. In this equation, what shall I do? I'll replace the value of P here. I'll replace the value of P here, okay? Then I'll get the relationship between volume and temperature. Volume and temperature in a adiabatic case we are discussing, remember, not isothermal. So here I'll replace P. So by replacing P, I'll get that R T upon V, and this is V to the power gamma is constant. Now this will be T V to the power, this is V. So if it will go up in the numerator, it will become V to the power minus 1. So it will become V to the power gamma minus 1, T V to the power gamma minus 1. And I'll divide this R in the right side. So K by R, this is a constant. So I can write final expression T V to the power gamma minus 1 is a constant. Okay. So here in this video, what we have learned, we have derived completely the three equations or three relationships between pressure, volume, and temperature in case of a adiabatic system or in a adiabatic process. So again, I am summarizing what we have discussed, and we have used here first law of thermodynamics and the concept of ideal gas equation here, and we have used them to find out the relationship between the three. So very important relationship. First one we have done, that is P V to the power gamma is a constant. And second one we have done, the P to the power 1 minus gamma T to the power gamma is a constant. Okay, is a constant, another constant, not. So third one is T V to the power gamma minus 1 is also a constant. Okay, so these are the three relationships we have discussed in this video and we have completely derived it. Okay, so thank you for watching this video. You can practice this relationship. It comes in the exam sometimes, and the problem based on these concepts come repeatedly in different entrance examinations also. Okay, so let's stop here for this video. We'll meet again in another video. Thank you.